glad to see we do have a full class today, so that's very heartwarming, thank you. I'm sure you're all fascinated by acid-base physiology. And so that's really our topic for today. And obviously it's a chalk talk, so what I'm going to try and do is sort of develop these concepts rather slowly. There are no slides, the lights are on. If someone has a question as we're going through, feel free to raise your hand and ask. If you have a question, it's likely your neighbor has a question and is just embarrassed to ask, so don't be shy. All right, so we're going to talk about acid-base, and we'll remember how do we quantify the level of acidity in any solution. We'll remember this, right? From high school, I hope, you've all learned that when you're talking about acidity, you're really talking about hydrogen ion concentration, correct? All right, so I just want to remind you of some definitions. Does anyone know how pH is defined? Because we've all measured the level of acidity by using a pH test strip, right? And then figuring out what pH. So anyone know what the definition of pH is? Wow, look at that. Right, so pH is the negative log of the hydrogen ion concentration. And that's probably an overly simplistic statement. I've been reading a little bit about this yesterday, but it still works quite well for our purposes. And this definition, some interesting history to it. It was defined, I think, in 1909 by someone named Sorensen, who, anybody know what he did? He was a master chemist at what was called the Carlsbad Laboratories. Does that name sound familiar, Carlsbad? Yes, the breweries ran some of the major chemists. And so he was the master chemist in the Carlsbad breweries. And he decided to come up with this definition for pH to define the level of acidity. And so one question that always perplexed me is what was wrong with just using hydrogen ion concentration? Why did he have to come up with this new scale, the pH scale, which is what we're used to? And so I'm not sure I know the answer. His article from 1909 is not written in the English, so I can't read it. But as I'll show you in a minute, if you look at the scale, the pH scale, which you're used to, runs from 0 to 14-ish, right? If you translate and actually look and see what the hydrogen ion concentrations are that go with it, they range from 10 to the -1 all the way to 10 to the -14. And that's a very, very, very large range of hydrogen ions, and it makes it very hard to work with if you're quantifying different structures, or in our case, looking at human physiology. And so it's much easier to work with a pH scale going from 0 to 14 rather than going 10 to the -1 to 10 to the -14. The other thing, and I'll show you this in a second, is if you look at the pHs at which body fluids are at and intracellular pHs, those are really nanomolar quantities of hydrogen ion. And minor nanomolar shifts in hydrogen ion are causing changes in pH that we find to be very important. And it's much easier to think in pH rather than in these other very obscure small quantities. And so what I want to do is let me just build a quick table here just so we can define some hydrogen ions and their corresponding pH. And let's see if I can do this. So anyone remember what the neutral pH is?
Sorry, do you mind just moving a little, a little bit to the right, just because we're blocked off against the board?
Sure. Am I good here?
Yes.
Is that good? Everyone can be down in the front here? I was trying to maximize my real estate. Now you can elbow me. Okay. Anyone remember what a neutral pH is? Okay, sounds like a good number to put on the board, right? Well, I gotta get my cheat sheets. So we have a pH of 7, and if pH is negative log of the hydrogen ion concentration, I think you can appreciate this is going to be 1 times 10 to the -7th hydrogen ion concentration. Now, the pH is a log scale, right? So if I change my hydrogen ion concentration by a factor of 10, say I increase it to 1 times 10 to the -6. Am I writing large enough for people in the back? Yes?
No.
Okay, so if I increase my hydrogen ion tenfold, if I'm working on a log scale, that's going to have a 1 unit change in pH. So my pH here is going to be 6. Similarly, if I decrease my hydrogen ion concentration tenfold and make it 1 times 10 to the minus 8th, then my pH is going to change and go up to the value 8. Right? And that's just the factor. This is just showing you the impact of the log scale on pH. All right, so let's fill in. I want to fill in some numbers between 7 and 8. And I'm going to try to choose some values really to frame a physiologic range that you will see in patients, but just really help us facilitate much of the discussion in this lecture. So does anyone remember the normal pH in the blood? 7.4. Okay, sounds like a good number to put on the board, right? So why don't we put a value of 7.4. And the hydrogen ion concentration for that is 4 times 10 to the minus 8th. And what I'm going to want to do is I just want to bracket that a little bit so we can talk about a range of pH going from below normal to high normal during our lecture. And so I'm going to put a value down of 7.1, a value of 7.7, and let me just get the corresponding values. This is going to be 8 times 10 to the minus 8th. And this is going to be 2 times 10 to the minus 8th. Okay. So far, so good. So we're going to really work a lot around these pHs between 7.1 and 7.7 throughout the rest of the lecture. Now, to begin our kind of analysis of how we evaluate patients, what I want to do is let's come up with one of our classic physiologic thought experiments. Let's say I take a beaker of water, and this is just pure water. So let's say I take a beaker of pure water. Yesterday it was like the thunder coming down on our heads. So, and let's say I have it in a room where I have carbon dioxide in the atmosphere. So I have some carbon dioxide molecules floating around in the atmosphere above the water. So if I set this beaker of water up in that kind of an atmosphere, what will happen? Well, I'm going to have a partial pressure of carbon dioxide in the air. I'm going to start initially with no carbon dioxide in the water, and therefore the partial pressure in the water is going to be 0. And so some of the carbon dioxide will enter solution into the beaker and eventually equilibrate with the PCO2 that's sitting above it, correct? Now the question I want to ask you is, once this is fully equilibrated, what would the CO2 content, what would the CO2 content of the water be? How would we derive that? So you actually know the answer to this. You've learned about Henry's law at some point in life. And so you know that if you want to calculate the CO2 content, you multiply the PCO2, partial pressure, times S, which is the solubility coefficient for CO2 in water. Right? And I'll put up here just for a moment, I'm just going to list the value of S, because we're going to need it later. The value happens to be 0.03. And so for any partial pressure, one can go ahead and calculate the CO2 content. Now, if we think about the experiments, now our water is equilibrated. The CO2 is now entered solution and exists as a partial pressure. And the next question I want to put out is, what happens to that CO2? Does it stay in the water as carbon dioxide, or does something happen to it once it enters solution? Now, what do you say? I know I'm kind of very simplistic, and I think about, I put salt in my water or sugar in my water, and it just dissolves. But it doesn't become chemically transformed. Unfortunately, carbon dioxide's not that way. And carbon dioxide can undergo a chemical reaction with the water molecules. And so what can happen is CO2 can combine with water to form what's called carbonic acid. Right? And that carbonic acid, in fact, is not terribly stable. And it can then dissociate into a hydrogen ion and a bicarbonate ion. Now this reaction, I think, was shown to you. You may not have recognized it, but if you look back in the I think it was the diffusion lecture where Dr. Oppenheimer talked about how CO2 is carried in the blood. He showed you how CO2 can cross cell membranes and then combine with water and undergo this transformation. He in fact told you that CO2 in large part is stored in the blood as bicarbonate. Now, the other thing I'll just tell you as an aside, the first step in this reaction is really quite slow. Okay, and if I put this in a beaker of water, that's a very slow reaction. In the body, this reaction is very, very important, and we have an enzyme called carbonic anhydrase, which I'm just going to abbreviate with a CA, and that speeds up the reaction, I think, approximately 600-fold. And so this reaction occurs quite readily in our patients. Now, if we look at this reaction, if you think back to my lecture yesterday, I said we're going to do acid-base analysis, and we want to use three values that come off the blood gas machine to analyze acid-base status in patients. We want to look at the pH, which makes sense because that's the level of acidity. And we want to look at the pCO2, and we want to look at the bicarbonate. Those are the three elements I said we were going to analyze. If we look at this reaction, we in fact have all of those elements present. I have a hydrogen ion, which relates back to my pH. I have a CO2, which relates back to my partial pressure of CO2 that I measured on my blood gases. And I have a bicarbonate. So this hydration reaction through carbon dioxide is the basis of everything we're going to do in terms of acid-base analysis. The problem is it's not really obvious how one would use this reaction or this equation right now to analyze a patient. And so in fact, what I have to do is I have to do a little bit of algebraic manipulation of that equation to make it in a form that we can use clinically. And so what I'm going to do is I'm just going to go through the algebra. I'll highlight for you what it is you need to know, but just bear with me as I go through the algebra for a second. I'm not expecting you to do this on the exam, but I don't want to show you the end result without showing you how we got there. Okay, so let's see what we want to do. Well, you have to go back to chemistry. And we remember every time we have a chemical reaction, we can write, there's an equilibration constant, right? That goes with that. And that can be written out as a mathematical expression. So if I look at, say, the right-hand reaction, I can have a constant, which I'm going to call K prime A. And that's going to equal the product of the hydrogen ion concentration times the bicarbonate concentration. Divided over the carbonic acid, right? So far, so good? All right. Okay. If we look at this, we should make this a capital A. We're really done with a capital A. All right. So if I look at this is getting me close. I have a hydrogen ion concentration, I have a bicarbonate, I have a carbonic acid. I don't really want to have carbonic acid when I analyze patients because I don't measure that. I measure CO2. So I want to reformulate this a little bit. And if I come back to my hydration reaction, clearly there's another constant for the left-hand side of the reaction, right? But in fact, I could probably have one constant to summarize both steps if I choose to. And I can just call that Ka. Take out the prime to distinguish that I'm not just talking about the right-hand side, but I'm talking about both steps simultaneously. And now I'll have the hydrogen ion times the bicarbonate divided over the CO2 concentration. And that's just looking at the final step relative to the first. All right, so this is starting to get me close, because now I have an equation that only has my three factors that I want to use to analyze patients. Now when I measure blood, I have to go a little bit further, because when I measure blood, do I measure hydrogen ion concentration, or do I report it out as pH? It gets reported out as pH, so it would be nice to formulate this not in terms of hydrogen ion concentration, but rather pH. Now to do that, I just look back over and I say, well, if I want to get hydrogen ion to pH, the first thing I have to do is take the log, right? So let's take the log of both sides of the equation. And I'll get the log of Ka is equal to, now you all remember that the log of a product is the same as the log of one term plus the other. So I'm going to do two steps in one here. I'm going to say the log of the hydrogen ion concentration plus the log of the bicarbonate over the CO2. Everybody okay? Perfect. All right. Well, pH is not log hydrogen, it's negative log hydrogen. So, well, if I subtract it from both sides of the equation, I move it over to the left, that'll give me a negative log hydrogen ion on the left. And I can just call that pH. I then move the log Ka to this side. And if I have a negative log Ka on the right, well, I can call that pKa plus the second half of that, the log of the bicarbonate over the hydrogen ion. No, the CO2, sorry. All right, almost there, right? There's only one last step we have to do. I measure pH on my blood gas. The blood gas machine will give me the bicarbonate concentration, but it doesn't give me CO2 content. It measures pCO2. So the last step I need to do is just change this from CO2 content to pCO2, and the way to do that is written right here. So, if pH is pKa plus the log the bicarbonate times divided by 0.03 times the pCO2. All right. Now I have a beautiful equation. I measure the pH, I measure the bicarbonate, I measure the pCO2. The pKa is a constant that's known. And so I have everything I need to analyze my patients. This equation, if you open up your textbook, is called the Henderson-Hasselbalch equation. The big trivia question is, how do you spell Hasselbalch? It's absolutely not intuitive. It's got many L's in it that you wouldn't expect. I'm not going to write it out. You can all look it up in your textbook, because I'm going to run out of space in a moment. All right, so the things I want you to remember from this is, I think it's going to be very important for you to understand the hydration reaction. We're going to keep revisiting this throughout our pulmonary course, so understanding this is going to be very, very important to you. And as you'll see for the rest of the day, we're going to be working with the Henderson-Hasselbalch equation to analyze our patient's acid-base status. So this is going to be very important for you to know as well. Let's take a look at this equation for a little bit. And if you look at it, there's something that should be intuitively obvious, which is at any given pH, since the pK is constant, the pH is determined by this ratio. So the ratio of the bicarbonate to the pCO2 at the end of the day is going to dictate the pH in any patient that you see clinically. And so let's put some normal numbers on here for a moment. How far can I extend for these guys? Not much further, right? I'll write it underneath. How about that? Okay, so the pKa is 6.1. Bicarbonate concentration is 24, typically in the blood. And then I have 0.03 times, anyone remember what a normal pCO2 is? 40. So if we work this out, 0.03 times 40 is 1.2. 24 divided by 1.2 gives me the ratio of 20. I can't do logs in my head. I will tell you, though, that the log of 20 is 1.3. 1.3 plus 6.1 is 7.4. Okay, that's everyone sitting in the room right now. All right, let's get this out of the way for a moment. So why don't we... All right, so why don't we do something now? What I want to do is, why don't we just make some perturbations to, say, the bicarbonate and the pCO2, and let's see what effect it's going to have on pH. So what I want to do is I'm going to build another table. Is this podium in people's way if I start writing? Okay, so let's build a little bit of a table. I'm going to put, let's see, I can write a pretty big one. Let's put some pHs, some bicarbonates, and some PCO2s. And then what I want to do is, anytime I want to calculate a pH, I need to know that ratio of bicarbonate divided by 0.03 times the PCO2. So I'm going to make a column for that in my table also. The first thing I can do is I can just put in the normal values, just so we have that in my table. Make it 7.4. Bicarbonate 24, PCO2 40, ratio is 20. All right. So let's say, as a first step, what if I take the bicarbonate, and what if let's say I double the bicarbonate, and I make it 48. So let's put a 48 down here. This is as low as I'm going to get. I see one person who can't see. This doesn't work. Okay, so I'm going to put a 48 down here. Maybe I can raise that a bit so you can see it. So what will happen if I make the bicarbonate 48 and I keep the PCO2 constant? Well, if I double my numerator and I do nothing to the PCO2, it stands to reason that my ratio, instead of being 20, is now going to be 40. Right? If I want to calculate my pH, I then have to do the log of 40 and add that to 6.1. And the log of 40 happens to be 1.6. 1.6 plus 6.1 is 7.7. And let's do the opposite. Let's halve the bicarbonate to 12. Keep the PCO2 constant. When I do that, what will happen to my bicarbonate divided by 0.03 times the PCO2? I'll have 12 divided by 0.03 times 40. 0.03 times 40 is 1.2. 12 divided by 1.2 is 10. The log of 10, everybody should know that one. Everyone should know is 1. I love it. 1 plus 6.1 is 7.1, right? So these are very simple perturbations. If I halve and I double the bicarbonate, you can see how we can quickly modify the pH from 7.1 to 7.4. So why don't we do one more thing? Why don't we now start modifying the PCO2 and see what happens? So let me make another, let's put up another set of data for a PCO2 at 80. No, let's keep going. I'm going to make a PCO2 at 80. What I want to do is I want to keep the bicarbonate constant now. So let's keep it at 24, our normal value. And let's say I make my PCO2 80, and I'll ask you, what do you think happens? Well, this sounds almost childish at this point, right? But it's not, because the temptation is to plug it into the equation. It's at 0.03 times 80, which would be 2.4, and then 24 divided by 2.4 would give me a ratio of 10, and the temptation would be to say that the pH goes to 7.1. And in fact, this is correct if I'm dealing with a beaker of water. Unfortunately, your blood is not a beaker of water. Your blood has buffers that are present in the blood. And what will happen in this circumstance? So remember, if I put some buffers in here, what will happen as I increase my CO2 to 80? Any ideas? Well, let's think about this. I convinced you that once I add the CO2 to water, I'm going to form some hydrogen ion, right? And so the minute I start forming hydrogen ion, that's what's causing the pH to drop in the blood, right? But what do buffers do when that happens? Buffers don't want to leave that hydrogen ion in solution. They're trying to buffer the change in pH. So these buffers will bind the hydrogen ion and form these H-buff complexes. They're going to form their conjugate base, right? Now let's think about this for a moment. How much does this happen? I'll tell you that in a beaker of water, if I don't have the buffers, I said a trivial amount of hydrogen ion is produced. I've already given you enough information to tell you how much hydrogen ion that is. Without buffers, the pH would go to 7.1 from 7.4, and that change corresponds to 4 times 10 to the minus 8th change in the hydrogen ion concentration. The hydrogen ion went up 4 times 10 to the minus 8th, and the bicarbonate had to go up equimolar, and that's 4 times 10 to the minus 8th. That's a decimal with 7 or 8 zeros before the change in the concentration. That's not measurable in patients. However, in the body, it's not water. Buffers are there. It removes the hydrogen ion from the solution and allows the reaction to move more and more to the right. And so now we start generating some bicarbonate. And we can generate measurable quantities of bicarbonate because of the presence of the body buffers. Now, does anyone know what these buffers are? So probably the most important buffer is hemoglobin. So hemoglobin is a very important buffer for the blood. There are a variety of other substances, maybe some inorganic salts, some proteins, etc., that can act as body buffers. I don't really want to talk about each individual one. I just want to kind of conglomerate them all into this term I'm calling buff minus. All right? And so all of those buffers will act to remove the hydrogen ion, and that results in some generation of bicarbonate. Now, this causes a little bit of a problem if you think about it. At the beginning of the lecture, I want to analyze acid-base status using pH, bicarbonate, and PCO2. But if you look at what's happening in this hydration reaction, bicarbonate could be influenced by 2 separate processes. If I change the PCO2, I will impact on a change in bicarbonate, which I've just shown you. But what if I have a metabolic process? You guys have, is diabetes still a pillar? Have you learned about ketoacidosis yet? Fabulous. So what happens in ketoacidosis? Oh, you've been tested on it already, right? You'll revisit it for this test now. So what happens is you produce the keto acids, right? And that's essentially adding hydrogen ion from that metabolic process, right? As soon as that hydrogen ion enters into the blood, it's going to bind or titrate to bicarbonate. So bicarbonate will change due to that metabolic process. So I have bicarbonate changing from 2 different pathways, either from metabolic processes like diabetic ketoacidosis, or other, I can list off many, many diseases, or they could be changing due to changes in the PCO2. And that causes a little bit of a problem in us wanting to analyze the acid-base status of our patients. And so what I want to do at this point is I want to give you sort of a graphical approach to deal with this problem of 2 competing sources for bicarbonate at the same time. Now before I do that, I have to ask you all a question. So I want to do my acid-base analysis just by focusing on this hydration reaction, right? I have other buffers that are present in the blood. So the question I'll ask you is it valid for me only to measure PCO2, pH, and bicarbonate to analyze body acid-base status? Or do I have to measure all these other buffers at the same time? Can I get away with that? I have a very complex system, and I'm only choosing to measure 1 salt. That's a perplexing question. So it turns out, obviously you can, otherwise we wouldn't be here today. And the reason you can is these buffers all have to exist in equilibrium with one another, right? And so any change that happens in one acid-base conjugate pair has to be paralleled and changes through all the acid-base conjugate pairs.